So, what if I told you that the exact same simple idea can explain how water drains from a tank, how a factory robot moves with perfect precision, and how your home's thermostat works? It sounds kind of crazy, right? But it turns out engineers have a secret weapon, a universal model they use to understand and control pretty much everything. Let's dig in and figure out what it is.
All right, here's our game plan. We're going to start with the secret weapon itself. First, we'll break down the two key ingredients. Then we'll see how this one idea applies to liquids, to air, to super powerful hydraulic machines, and even to something as abstract as heat.
Engineers have a massive challenge. The world is just full of these incredibly complex, always changing systems. Now, to control any of them, you have to understand them first. But trying to model every single system from scratch, that would be an absolute nightmare. So they came up with this incredibly smart, elegant solution. And here it is. This is the big secret. Engineers model almost everything using just two core concepts, resistance and capacitance. That's it. By thinking about the world in terms of these two simple ideas, they can predict and control systems that, on the surface, seem to have nothing in common. So what are resistance and capacitance, really? Well, to get it, we don't need any complex math or crazy equations. All we need is a simple water tank. It's the perfect analogy, and it's going to help us build this whole idea from the ground up. Okay, first up, resistance. Just think of it as anything that gets in the way of flow, like a bottleneck. For a water tank, the resistance is that narrow drain pipe at the bottom. The skinnier the pipe, the higher the resistance, and the slower the water drains out. It's really that simple. Resistance restricts flow. And the second piece of our puzzle is capacitance. This one's all about the ability to store potential. In our tank, the capacitance is just its width. Think about it. A really wide tank has a ton of capacitance. You have to pour in a lot of water just to make the level go up a tiny bit. A skinny tank? Not so much. So in a nutshell, capacitance is storage. All right, we've got our toolkit. Resistance, which restricts flow, and capacitance, which stores potential. We've seen how it works for a liquid system like our water tank, but what about something totally different? What about a system that uses compressed air? These are called pneumatic systems, and they're all over the place in factories and automation. And this is where the light bulb really goes on. For a water system, potential is the water level. For a pneumatic system, potential is air pressure. The resistance goes from being a narrow pipe to maybe a valve. The capacitance goes from being the tank's area to the container's volume. See, the names change, but the concepts are exactly the same. We're still just talking about storing potential and restricting its flow. And there's a really good reason these pneumatic systems are so common. I mean, they run on air, so they're naturally safe in places where even a tiny spark could be a total disaster. Plus, they're simple, they're tough, and they're easy to fix. That's why you see them on practically every factory floor. So, understanding a system with this model is one thing. That's cool. But controlling it? That's where the real magic happens. The next step is to use that model to build a controller, a device that can automatically manage the system. This is how we go from just theory to an intelligent machine. A classic example is something called a nozzle flapper. It's an incredibly clever little device. A tiny, almost effortless movement of a little flap is sensed. This tiny motion causes a huge change in air pressure, which amplifies the signal. That new, powerful pressure can then be used to move a massive valve. That's the act. A tiny little input creates a gigantic output. And don't think this is just some old-timey invention. This simple sense-amplify-act logic, it's the conceptual foundation for the most common control algorithm in the entire world, the PID controller. The brains inside your car's cruise control, inside huge industrial chemical plants, they're all based on this fundamental idea. Okay, now let's take our universal model and apply it to the heavyweights, the real powerhouses of the engineering world, hydraulic systems. They also use resistance and capacitance, but they operate on a whole different level of power. So what's the big difference between the two? It really comes down to the fluid they use. Pneumatics use air, which you can compress. It's fast, but not great for raw force. Hydraulics use oil, which is pretty much incompressible. And that lets them operate at incredibly high pressures and generate just immense power. We're talking bulldozers, aircraft landing gear, that kind of stuff. Just to put that into perspective for you, the tire on your car is probably around, 35 psi? Hydraulic systems often run at 5,000 psi. Some even go up to 10,000. That massive pressure is what lets a little hydraulic cylinder lift tons and tons of weight like it's nothing.
And that high pressure gives hydraulics some incredible advantages. You get these huge forces from really small components, and the response is almost instant. The oil itself keeps everything lubricated. And maybe one of the coolest features, you can stall a hydraulic motor under a full load, like a crane holding a giant steel beam in midair, and you won't damage a thing. Try that with an electric motor.
Okay, so we've seen our model work for liquids, for gases, for high-power oils, but what about something that isn't even a fluid? What if we push this analogy to its absolute limit, the flow of heat?
It's almost hard to believe, but it's absolutely true. The way heat moves can be perfectly described with our R&C toolkit. Things that resist the flow of heat, like the insulation in your house, that's just thermal resistance. And materials that can store a lot of heat energy, like a big cast iron skillet, that's thermal capacitance. The exact same principles apply. And that brings us right to the core of this whole idea. Whether we're talking about water level, air pressure, or temperature, we're really just describing one thing: potential. And every single one of these different systems can be understood by how it stores that potential, its capacitance, and how it restricts its flow, its resistance. You know, once you start seeing the world through this lens, you see it everywhere. A bank account that slowly builds up and then gets spent. The charge on your phone's battery draining away. Even the stress building up before a big deadline. So I'll leave you with this. Now that you know the engineer's secret weapon, what system in your life looks just like a tank with a drain?